Hi, yes, Aritra sir and Rajdeep sir, may I start?
Ma'am, I have made you and Aurithro sir both as a presenter.
Thank you very much.
So,
Thank
ma'am,
you
you
very
can start. Thank you. Yes.
Can you see the slide?
Yes, it is visible.
Okay, fine.
Yes, ma'am, it is visible.
So,
Ma'am, we can see the.
hi, yes.
Yes, ma'am, we can see the slide. Sorry to interrupt, ma'am.
Thank you.
Slide is visible, ma'am.
Okay, thank you. So, as you know, this today the experiment is the first one, that was the network theorem part 1, in which we have covered up. We will cover up the verification of superposition and Thevenin's theorem. Okay, so to here experiment 1 and 2 cover. Four theorems have been divided into two parts into this experiment number 1 and 2. So today we are going to explain or demonstrate you the experiment number 1, that is verification of superposition and Thevenin's theorem. Now, what is the statement for superposition theorem? So first of all, as we have already discussed with you, that superposition theorem is valid for the linear system, for the system where the homogeneity and superposition principle holds good. So here and not only that, a bilateral network also. The network should also be any bilateral, any linear bilateral network. So linear means homogeneity and superposition will be obeyed, and bilateral means current can flow in both the direction in any branch of the network, right? Achha. So first of all, let me explain this linearity property. So linearity property is the property of an element describing a linear relationship between cause and effect. Okay. And a cause and effect means suppose voltage is provided to a network, and therefore there is a effect is that the current is flowing through that network. Okay, so that is it is better explained with the Ohm's law. So and next is the homogeneity property, is that suppose the cause is being multiplied, the effect will also gets multiplied with the same factor. Understood? And additive property is that superposition property. That means if suppose one input is provided to the system, the output is, suppose input U1 is given to the system, output is Y1. Input U2 given to the system, output is Y2. So when U1 plus U2 or U1 minus U2 will be provided to a system, okay, as input, okay, so the effect will be, if U1 plus U2 will be given, then the output will be Y1 plus Y2, or if U1 minus U2 is provided to the system as input, then the output will be Y1 minus Y2. So that is called the, what should I say, the additive property. Okay, so algebraic summation of the effect when the causes are acting individual. So individual effect, algebraic summation of the individual effect of the causes will be the net effect when they will act simultaneously. Achha. So in any linear bilateral network, the current at any point of the circuit or the voltage between any 2 points of the circuit, due to the simultaneous action of more than one input, more than one voltage sources or current sources which were being under consideration for that particular observation, is the sum of the, or algebraic sum of the components, currents or voltage in a network is that due to one source acting alone, that is individually they are acting, and the other sources being replaced by their respective internal resistance. So when one source will be considered, then the other source will be replaced by their internal resistances. Okay, so their combined effect will be algebraic summation of their individual effect. Achha. So here let me write it like this: Y, which is say better say suppose E1 is the individual input to the system. So Y1 is equal to K into U1, and when U2 is applied to the system, Y2 is equal to K into the output, Y2 is equal to K into U2. Now suppose alpha U1 plus beta U2 is the input to the system. So obviously the output will be nothing but alpha Y1 plus beta Y2, which can be written as alpha K U1 plus beta K U2. Now alpha beta are any constants. Understood? So this is the algebraic, it is the mathematical representation of the superposition principle. So that also has been written over here. First, this homogeneity property. Say input, we have V is equal to IR. Now suppose the V is multiplied with K, so here I also gets multiplied with K. Next is, say V1 is the input and therefore I1 is the output. Okay, so we have written V1 is equal to I1R, and similar way when V2 is the input, I2 is the output. So V2 is equal to I2R. Now you can think in opposite way also. I1 is the input, so output is V1. So V1 is equal to I1R. If I2 is the input, so V2 will be equal to I2R. Now when input is applied as I1 plus I2, then what would be the resultant effect? That is written as V, which is nothing but V1 plus V2. Okay, so here we can say that a resistor is a linear element because the voltage current relationship satisfies both the homogeneity and the additive properties, and in general a circuit is linear if it is both additive and homogeneous. So a linear circuit consists of only linear elements, linear dependent sources and independent sources. Now coming to the experimentation. Okay, so first of all, illustration of a network, and that type of network only we will consider in our experimentation. We can have any type of networks because we have seen in the theory classes that many examples have been considered, and there we can go for any type of network, and if this network is linear bilateral in nature, then it obviously obey the superposition principle. So it's a simple network we have taken here. Two sources have been considered. You can see over here VA and VB, and three resistances are connected. What are the resistances? R1, R2 and R3. Now branch voltages is R, V1, V2 and V3 across respectively R1, R2 and R3. So current flowing through R1 is I1, current flowing through R2 is I2 and current flowing through R3 is I3. So we need at least 3 ammeters to measure this I1, I2, I3 and voltmeter to measure V1, V2, V3. Now when we are talking about the superposition principle, we will first apply the apply these two simultaneously, and we will measure all these three currents and voltages, right? Now next, what is the task? We will first omit this part. So it would be replaced with its internal resistances. So that is uh, drawn with this green lines. Now if it is ideal voltage source, so its internal resistance will be 0. So that means it would be nothing but CD will be shorted. Now the first of all VA considered over here. So say let's the effect here, current flowing through R1 is I1A, current flowing through R2 is I2A, and current flowing through R3 is I3A. Okay, next task is to omit this VA and insert the VB in its previous position. So VA, if VA is the ideal voltage source, so its internal resistance will be purely 0. So what will happen? So AD will be shorted, right? So AD shorted over here and VB applied. So effect current is I1B, I2B and I3B. Now what superposition theorem states? That I1 should be equal to I1A plus I1B, I2 should be equal to I2A plus I2B, and I3 should be equal to I3A plus I3B. And that we will see through experimentation. So look at here. First VB acts. First VA acts with VB replaced with internal resistance. Okay. Next VB acts with VA replaced with internal resistances. So in both the cases, we will measure all the branch currents and we will get the algebraic summation of this currents, and we will check whether they are coming as same as the currents when both the sources are applied simultaneously. Auditya sir, do you want to add something over here?
No, madam, it is okay.
So look at here. Hi, yes, Auditya sir.
No, it is okay, madam. You can continue.
Okay, thank you. So look at here, we have considered in our laboratory the VA to be of 0 to 10 volt and VB to be 0 to 30 volt. Or you can interchange the position of these two, no problem at all. But you have to keep it in mind that when you will put again, so they will be placed at their previous position only, right? So it is like that, and 3 ammeters are considered over here. Okay, so they are connected in series with the resistances. So therefore, the ammeter to measure the current flowing through R1 is in series here. For measurement of I2, this ammeter A2 is in series, and this A3 to measure the current flowing through R3. So connect the circuit as shown in this figure with the resistance as suitable value. Note the reading of the 3 ammeters. Now disconnect one of this voltage source and measure all the 3 currents when only one source is acting. Next, just disconnect that particular source and connect the other source at its previous position and get the readings of all these 3 ammeters, and then go for algebraic summation of these currents. Let me start this.
Only thing here I want to add that when we were doing experimentation that time, we missed out to record exact value of that. Whether we put exactly 10 or 30, that I don't remember. So
Yes. We have not kept it at 10 or 30. Yes, also sir, you are correct. You are correct.
So if you people try to solve it mathematically, like the way you solve, and then try to valid with your experimental result, you may not get the same because we forgot to record the voltage value which we use for the experimentation.
Yes. That's true. Achha, now how I can start it? Also, sir, may I start?
Yes.
Audible?
No, ma'am, the
Yes,
video
ma'am,
is
you're
not
audible.
audible.
Not audible?
The video is not
The
audible.
video,
Your voice is.
Sir, your voice is,
The
ma'am, your
video
voice
is
is
not
audible.
audible.
Video is not audible,
You
ma'am.
are audible, but
ma'am,
What?
share with computer audio.
Share with computer audio.
Or you can explain with the video.
How can I share? Arito sir,
It is it. Do you have your MS Team app in your laptop?
MS Team app.
I mean, through the software actually. You are trying to present through web mode, no?
Ha
Through
ha
the
ha
web.
ha.
Uh,
Yes.
Maybe because of that, I don't know. Last day, Aniruddha sir asked me to do like that, install the software and then run through it. In that time, it didn't show any problem. In the setting part, can you just adjust the sound? I don't know whether
Setting
yeah,
part.
the sound
Device
setting
settings.
part. Device
Yes, ma'am.
setting.
Device settings. There is sound.
Speaker is at high.
Ma'am, you should
Ma'am.
not share the whole screen, ma'am. You should share only that tab which you are showing.
Ma'am, please stop sharing and again start sharing. There will be option with audio or without audio.
Acha, chal, let me. Acha.
Yes, ma'am.
Stop sharing. Next is
Ma'am,
And
please
again,
start
sharing.
button.
start.
When you click, you will get three options, ma'am. Select whole screen or select a particular tab like that.
Then
And
what to do?
then there will be option with audio or without audio. Then you have to select with audio.
That option will come when you select only a particular tab, ma'am. I mean, the particular tab which you are going to share now. The video
Yes.
tab.
Presenting.
Now once start the video.
Gotcha. Audible. Is it audible?
No, I'm still not audible.
No,
No,
ma'am.
ma'am.
No, ma'am. Still possible.
Ma'am, just remove your earphones and then it will come. Matlab
My ear.
unplug. Yes, unplug your earphones. Then from your mic, your this audio will come.
Okay, I got your point. But it is not.
Yes, ma'am. Now
Yes,
audible.
ma'am.
But
Yes, ma'am.
But
But it
not
is
loud.
very low.
But not clear.
Ma'am, it is not clear though.
It is not clear.
Increase your laptop's volume.
No, laptop volume is very low. That's why I'm wondering. It is 100%, but it is very low. Arthur sir, what to do?
I'll do one thing. I'll just try to play from mine. Let's see what happens.
That will be okay, ma'am.
Actually, let me first.
Ma'am, you can stop sharing and Aditya sir or Rajiv sir start sharing so that we can see and hear.
Yes. I have stopped sharing.
I am trying to share the video. Just
Yes.
I cannot share it as a tab. I don't know. When I'm trying to share. Okay,
No,
then window or
window.
Superposition theorem and then Thevenin's theorem. So coming to the superposition theorem, we are having the circuit as shown in this.
Click on the window.
It is having three
in
resistances
window it is
with
not
three ammeters
showing the
that use
file. I
the
don't know.
current
Let's see.
of these three branches that
But audio is coming.
this R1.
Yes, sir. Audio is coming.
Is it visible?
And there are two sources.
Yes, sir. Now it is
One source
not
is
visible. Your screen is visible. MS Team screen is visible.
MS Team.
Yes,
No,
sir.
audio can you
Yes,
hear?
yes, sir.
Audio
Audio
is
is visible.
shown over here, and the second source is this. Now you can see.
But not the video, sir.
The first source is
Video.
7.7 volt, which we are keeping.
No, I can't hear actually. Audio is coming, but video is not showing. Is it?
Yes.
Yes.
Yes,
Yes,
sir.
sir.
Yes.
So what I am trying to do, I am when I am trying to share, I'll just stop share and then.
Sir, at
Desktop.
first start sharing and then there will be option include system audio. You have to tick on it and then select desktop.
That is happening when we have installed your MS Team.
Oh, just wait for a minute. Just wait for a minute. Just wait. Let me share it.
Okay, ma'am.
Good afternoon, students.
Audible.
Yes, ma'am. Yes, ma'am. It is audible.
Sir, ma'am, audible and visible.
Good afternoon.
Ma'am, it is okay now.
We are going to demonstrate the network theorem 1, that is for superposition theorem, and then Thevenin's theorem. So coming to the superposition theorem, we are having the circuit as shown in this figure. Can you see this figure? It is having three resistances with three ammeters, which are used to measure the current. These three branches, that means current flowing through this R1, R2, and R3, and there are two sources are connected over here. One source is this, another is this. You can see here in the experimental setup, these are two sources. This is the first one as shown over here, and the second source is this. Now you can see here the first source is showing 7 volt, which we are keeping, and here the second source is 5.5 volt. Okay, now I'm coming to the connection. What is the connection? First of all, you can see over here. Good afternoon, students. Today we are going to the current of these three branches. These are two.
What is happening?
Good afternoon, students. Today we are going to demonstrate.
Just wait for a minute. What is happening?
Good afternoon, students.
Also, when we are
Second source is this. And you can see here the first source is showing 7.7 volt, which we are keeping, and here the second source is 5.5 volt. Okay, now I'm coming to the connection. What is the connection? First of all, you can see over here.
It is not fully
Loaded.
fully loaded. Yes,
Yes.
just wait for a minute. Let me. Oh, just. Wait, just wait, huh? Aritra sir, it is not. I don't know what is happening.
You just tell me how could you play the sound, then I can start the
Just
video.
wait.
Sir, there is an
Let
option include a system audio. You have to click on
include system audio. It is here. Aritra sir, can you see a share content? Just write to that include computer sound.
Share content. It is there in
Presenting. And then include computer sound.
Sir, on the left top side, it will be.
Right top side.
Okay. Settings, na? There.
Settings na. Present. Presenting.
No, I am trying to do it from the web, not from the installed
Okay.
app. So it's not showing for me.
From the web.
There is MS Team. There is an option. Na? Either you can download the app or you can run it through web mode. So I didn't download it.
Oh, acha. It is downloaded version mine. But why the full video is not coming? That is I'm wondering.
You can do one thing, madam. You can run it separately. I mean, not in the PPT, but you have the video, na? So that file you run. I think. Then you can go back to again the slides.
Just wait for a minute. Presenting. Include computer sound. Acha. Next is a folder. Then verification of superposition. Can you hear?
No, ma'am. You have to select desktop after system audio.
It is
Whole
having
screen.
3 resistances with 3 ammeters
Whole
which
screen.
are
It is
used to
now
measure the
okay.
current of
Yes, ma'am. Yes, ma'am. It is okay, ma'am.
Yes, ma'am.
through this R1, R2 and R3. And here the second source is 5.5 volt. Source coming connection. What is first of all, you can see over here this A point is coming here and this is coming here. So we are giving the sources here across this 2 terminal. This 2 terminal is this. Now next is ammeter and this resistance. These two are in series. So what we have given, this is coming over here, then resistance, then resistance is these two are in series, resistance and ammeter. You can interchange the position. So first we are keeping the resistance, then the ammeter. So next this one is coming to the ammeter, and the ammeter from the another terminal of the ammeter, it is going to the next branch, that means this B point, right? So here it is the B point, right? So across this B and D, this is D point, this resistance is connected. This resistance, you can see it, this one is the rheostat. Here intentionally one rheostat is kept to show you how the rheostat is being connected. So it is the variable terminal, and you can see over here, this is the fixed other terminal. Okay. Now B terminal. Now from B terminal, what it is coming here. Okay. Now from this, it is going to this resistance R2, right? R2. Then from the other terminal of R2, to measure the branch current across R2, another ammeter is connected. So this one is the second ammeter. So this one is the first ammeter, which is measuring I1. This one is I2 and this is I3. So from the another terminal of the ammeter, it is going to the source. So you can see over here, it is going to the source, and the other terminal of the source, from the other terminal of the source, here it is connected here. So this point is next. Now to additionally here 2 resistances are kept, that is 30 ohm and 30 ohm. No need to worry about it because the same current is flowing over here. Now from across this terminal, it is going to here to measure the R3 I3 branch current, and from the ammeter, this terminal, it is going back. Okay, so this 3 terminal again connected. Understood? Achha. Now we are going to demonstrate the procedure. First, what we will do, when two sources are connected, this is the case when two sources are connected, we will measure all these three currents, I1, I2, I3. So here, I1 is showing 0.04 ampere, I3 is showing 0.06 and I2 is showing 0.02. So therefore, I am writing over here, I1 is 0.04. I am not writing the unit over here, I am writing over here. This is ampere, so 0.02. And this one, I3 is 0.06 when both the sources are connected. Both the sources. Let me proceed to the second run. What is that? When only V1 is connected.
V1 means VA.
So that means we have to short the V2. Let me short it. Okay. Now I am making it off. Every time you have to keep in mind that you have to make it off, and then we will do this. Now how I am doing this? Let me open this and sorry. See, this source is just isolated. Okay, removed. Now we are going to have the next set of reading. That means V1 is connected only, and we will measure all these three currents. So now I am making it on. Hey, sorry.
Quick, we can switch it.
We can switch it off. Now these are the measurement. That is I1A. Next is I2A, and this one is I3A. Okay, so let me write it out. I2A 0.03. So this is DC current. You can see the negative sign. This current flowing in the opposite direction. What we have assumed previously, this current is just the opposite direction. Okay, and it should be, because if only this source is connected and this source is not connected, so therefore the current should be in this direction. But previously, when this source is connected, the current is in this direction. That's why this is negative. Okay.
Students, are you following?
There should not be any confusion regarding that. So that
Student,
is
are you following?
when V1 is connected.
Yes, ma'am.
Only one run is
Yes, ma'am.
connected.
Okay, thank you.
Which will gives us I1B, I2B and I3B. Now let me redo the process. First, I'm connecting the V2 again in the circuit, in the network, and then I will remove V1 from the network. Look at here, it is being shorted. V1 is shorted. That means we are removing this one. Okay. This 2 points shorted. Okay. Now I am making it on. Remember that V1, V2, V3 value should not be varied during the whole experiment. Okay. Now let me measure.
That means two source value should not be changed.
This one is I1B. You see, it is flowing in the opposite direction with respect to the previous one. This is I3B. And that is I2B. All are in ampere. Now we are going to verify the superposition theorem. How? I1 should be equal to or close to I1A plus I1B. Acha, I1A is 0.06 and I1B is minus 0.02. What it is coming? 0.04 ampere. And look at here, I1 is perfectly 0.04. So we can write it here, verified. Right. Next is I2A and I2B. I2A is and I2B is 4 ampere, and I3A and I3B. I3A is 3 ampere. Now look at here. I2 is 0.02 and this is 0.01. That means it is close to this. So here also we can write it verified with little error. Similarly, it is 0.05 ampere and here it is found out to be 0.06. So here also these are close to each other. So therefore here also we can write it as verified. So with all this with this experiment we can say that superposition theorem is verified here perfectly, and in this too with little error. So in a nutshell we can say that this is the superposition theorem is verified satisfactorily.
Ma'am, actually there is 20% error, no ma'am.
Hi, yes, that is why this error comes. Can you tell us?
Because ma'am, we are taking it as ideal, but it is not ideal voltage. There will be some internal resistance.
Yes, very good. And also maybe due to the measuring unit also, what the measuring unit we are using, they are also fluctuating. So for that also it gives some error. Whatever I2, I3 value we have measured, actually they are fluctuating. So it may happen that 0.05 is actually 0.06. And it is digital meter. It is only after 2 decimal it is giving 2 digit only. Yeah. So it may happen that due to that error also it is giving some error. Achha. So this is, can you see this?
Yes,
Hello.
Yes, ma'am. Yes.
So this already explained to you. Okay. Next we move to Thevenin's theorem. Yeah. So what is Thevenin's theorem? Any two terminals of a network composed of linear passive and active elements may be replaced by an equivalent voltage sources. So what are the passive elements here? And what are the active elements? The active elements, the sources. And passive elements, the resistance and inductance or capacitors, what are included, what are being connected in this network. That can be replaced by an equivalent voltage source in series with an equivalent resistance. So this equivalent resistance is known as R Thevenin and equivalent voltage source is known as V Thevenin. The voltage source is very sorry. The voltage source is equal to the open circuit voltage between the two terminals. Okay, we will show you how to measure this open circuit voltage, and the series resistance is the equivalent resistance looking back into the network through the terminals across which the load is being connected with all other sources in the network replaced by their internal resistances. This is the, can you see this slide? Hello?
Yes. Yes, ma'am.
This is the circuit we have considered. So earlier also we have explained to you, I think in the first class. So it is like a bridge circuit, PQRS, this is. And additionally across A and C, this load resistance is connected. The load resistance you can vary. We have arranged in such a manner that the resistance RL can vary. Okay, now what is given, what is stated in Thevenin's theorem, that this whole network can be equivalently represented with this, where VThevenin is the equivalent voltage source. How to measure? That is, make the RL open and measure the voltage across A and C with RL open circuited, RL removed. So that the V Thevenin or V open circuit will appear across A and C. So that is V Thevenin. R Thevenin is that this will be shorted, or assuming this to be ideal voltage source, shorted this one. Now through this terminal, and remove this RL, through this terminal A and C, you look back into the network. You will find R Thevenin as the equivalent resistance. So can you tell me what would be the equivalent resistance therefore? Across A and C, what is coming? Do you have any idea? What would be the, if this is shorted, what does it mean? B and D shorted. So then B and D shorted. So P and R will be in parallel to each other, and Q and S will be in parallel to each other. And then this parallel equivalent resistance and this two parallel equivalent resistance will be in series.
R.
Okay, so that is R Thevenin. And then across this two terminal, actually, this two terminal is A and C, across which the RL is connected. Okay, so that is the equivalent circuit. So this is equivalent. This and this is equivalent to. Next, this is V Thevenin. How to measure V Thevenin? If you connect an voltmeter across this, you will get the V open circuit, which is V Thevenin. Next is R Thevenin. This one is shorted with zero internal resistance, so R Thevenin will appear across this. Okay, what I have just explained to you. So what we will do? First, what we will, with RL connected, we will measure. We will measure the current IL, right? Next, what we will do? We will open circuit the RL and we will measure the V Thevenin. Understood? Next task is to measure the R Thevenin. So for that, first of all, we will short the R Thevenin and we will measure the short circuit current flowing across this. So that will give you ISC. Next task is that keeping the RL connected in the circuit, we will vary the RL and we will get some values of VL and IL. And with this VL and IL values, we will plot a graph with VL as the ordinate and IL as the axis here. So we will take 4 or 5 data over here and then we will extrapolate this. So since VL, we know VL is nothing but V Thevenin minus R Thevenin IL. So this graph is nothing but a straight line with minus R Thevenin as its slope. Understood? Achha. So if we extrapolate this, it will cut this point at V Thevenin and it will cut this point at ISC. Why it is ISC? Achha. First of all, here why it is I short circuit? That means since it is the slope with R Thevenin, R Thevenin it is here current is 0. At y-axis, this point means current is 0. So when the circuit is open, we can get the current to be 0. That means RL removed. Understood? So that is open circuit voltage VOC, or we can say this as to be V Thevenin because V Thevenin is also the open circuit voltage. And what it is? When the voltage is 0, but current is flowing. So when the voltage is 0, when the voltage across RL is 0, when that means RL is short circuited at this moment. So this current is ISC. And you see this point is nothing but 0, V Thevenin, and this point is ISC, 0. So find out the gradient. What would be the gradient M? M is V Thevenin minus 0 by
ISC
0.
minus 0.
Nah, 0 minus ISC. For this point though. So 0 minus ISC. So what it is coming? Minus R Thevenin.
Yes, ma'am.
Okay. So extrapolate this, you will get this point. So this point will also verify you the analytically or graphically the value of the open circuit voltage, which is VThevenin. So by that way we will verify whatever VThevenin we have obtained experimentally whether it is correct or not. And similar way we will find out the ISC experimentally and VThevenin experimentally. So VThevenin experimentally divided by ISC experimentally will give you RThevenin experimentally. And from the gradient of this graph, we will find out, suppose, we will find out the RL. So analytical value of RL also, RThevenin also, we will find it over here, and that will give that with the experimental value. So if these are coming close to each other, then we can say that the Thevenin's theorem is verified. So that is what RL will be verified. An ammeter is inserted in series to measure the IL, and voltage across this will measure the VL. Alright, sir, may I start the video?
Hello? Yes, madam.
Acha. So you see here, plot VL versus IL graph. Gradually decrease RL till the lowest supplied value is exhausted for each RL, keeping V input to be constant. Plot VL versus IL graph and find the intercept VLO, that means open circuit voltage VLO, and slope RThevenin from the straight line graph, and measure the open circuit voltage VThevenin at the terminal CA, keeping VIN unchanged. So it is seen that if VLO is equal to VThevenin, then we can say that this theorem is verified experimentally. Achha. This is how to measure the VThevenin, and this is how to measure the short circuit current ISC. The RL is shorted, that means it is removed and it is connected, and this two terminals CA is connected through an ammeter, that means to measure the short circuit current. Now let me again, as previous, I am trying to show you the video. Sorry, every time I am opening the mail, present, stop, to this, then include this, then entire screen, then this.
Okay, so now
is this visible to you?
Is to verify the Thevenin's theorem.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Consider is this, it's like a grid circuit. It's having 4 arms P, Q, R, S. Now let me show you what are the P, Q, R, S over here. Now see here that the 2 nodes across P, that is A and B. So here this arm is considered to be P, which have 2 terminals A and B. Next is B and C, across which Q is connected. Okay, so this 2 point we have considered to be B and C terminals, and this is the Q. So let me write it over here. This is P, this is Q. Okay. Next is across C and D, S is connected. So C is considered to be this and D, and therefore this one is S. S. And which one is left? That is R, and which is connected across A and D. So A and D, and this one is R. Okay, there should not be any confusion regarding this base circuit. Now one thing is left, that is RL, the load resistance, which is variable. So this one is the variable resistance, which is this rheostat. Okay, and this is connected across CA. So this is C and this is A. And the voltage source, which is considered to be this one is connected across B and D. So let me show you how the connection is being done. So this source is connected across B and D. So we have connected here B and this is D. So this two has been connected like this. Okay. Now this D and this D shorted. Right? Another thing is that A and A shorted and another B and B shorted and C shorted and this C is also connected here. Okay, and this is A, another A terminal. Okay, so this one is shorted. Now ammeter is inserted here with RL. That means across C and A one ammeter is connected. So this ammeter is here. So this is connected across C and A. Okay, so across C and A it is in series. Okay, you can see over here it is connected, right? So this is C, this is A point.
Through resistor, through rheostat.
Through rheostat it is connected. Through rheostat it is connected, and across this load one voltmeter is connected. So that voltmeter is coming here. This is the voltmeter we are using over here. It is connected across the load resistance. Here it is the load resistance, right? So this is all about the circuit connection. Now what are the run? Run is first, we will set the rheostat at a particular value. Say we are keeping this at 50% value. Let me.
It's almost 50%.
It is almost 50%.
And it is a 100 ohm resistor, and we are at the 50% position, means approximately 50? Our RL has to be around 50. Okay.
Okay. This one is the. Okay. So this is 100 ohm resistor. So this. Now let me show you the ammeter reading as well as the
voltmeter reading.
Okay, so this is noted down. So for which we can calculate the RL, how? VL by IL. Next is our requirement is to have the V Thevenin or V open circuit when the load is being removed and when the load is zero, that is short circuit current. So if we move it to the so in between that also we need to take some readings. So for which we will kept it at 25%, 75% of the resistance value,
and the 100% also,
and 100% also, and for short circuit we will kept it at 0. Okay.
So now we'll short it.
We will short it. Okay. We have shorted. So you can notice it from the voltage value. It is coming out to be 0 since it is shorted. And this is the I short circuit. So everybody can note it down. It is 0.07. ISC, I short circuit is 0.07 ampere. Right? Okay. Next is
we have to now open it to
let me open it.
So that connection we are removing from here. So we have disconnected. Now it is an open circuit.
Open circuit. So you can note it from here. The current is 0. The current is 0.
And open circuit voltage
is?
It's fluctuating around 2.2, 2.3 like that.
So you can note it down. It is roughly 2.2 volt for the V Thevenin or V open circuit. Now for the complete run, we have taken all the data a priori and you can show it. That is different voltages, load voltages and different load current, for which you can have this. You can have this graph, right? You can have this graph. This is IL axis, this is VL axis. So since VL, IL, we have taken 4 data, you can have this data here.
And then join and extrapolate.
Join and extrapolate. So if we extrapolate here this side, so this is corresponding to IL equal to 0, and this obviously will be VOC. And in this point, if we extrapolate this, this is VThevenin voltage VL equal to 0. So this is nothing but your ISC. So this 2 point you will get it graphically. Now let me explain it. How do you verify this? So RL we have roughly having 43 ohm, that is VL by IL. Suppose we are going to,
and that is for 50% setting.
50% setting.
Theoretically it is 50 and we are getting 43.
So 50%. So now we are going to verify that whether 0.03 ampere load current is coming or not. How we will verify? This will be VOC by RThevenin plus RL. How we are getting RThevenin? That is VOC by ISC. So it is coming out to be 2.3 by 0.07, 32.85. So now VOC 2.3, RThevenin 43.33, RL is 32.85. It is coming perfectly 0.03 ampere. That means it is getting verified. The Thevenin's theorem is verified. Okay. So that is all about the Thevenin's theorem verification.
That's a student. Hello. Hello, student.
Yes,
Can you
yes,
hear
ma'am.
me?
Yes, ma'am.
Yes.
Yes, ma'am.
Now we will can you see the slide?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Data already we have written. Now graphically part. So we have taken all the 4 datas that we have tabulated here. Now with this we will plot. Right. Now this is this plot. If we extend this, extrapolate this, it will cut the y-axis, that is real axis, at near about 2.25 volt. We have got the VThevenin 2.3 volt. So it is nearly the VThevenin that we have got it. VOC we have got it. So experimental to 2.3 or 2.2, and here it is 2.25. So it is matching with this. If you extrapolate in this here, this side, so it will intersect with the x-axis. It is coming out to be 0.0725, and where experimentally we have got ISC to be 0.07 ampere. So these two are also matching to each other. Next, the question of RThevenin. Okay, how do you get this? So we will find out. We will drop a perpendicular over here from this point, and we will draw an horizontal line from this. It will cut at this point. So this length is nothing but delta VL, and this length is delta IL. So what is delta VL? This one is 0.02 and this one is 0.04. So length is 0.04 minus 0.02, that is 0.02. And delta IL is 1.6 minus 1, that is 0.6. So 0.02 divided by 0.6. This one 0.02. Very sorry. 0.6 divided by 0.02, because this is y-axis and this is x-axis. This is V and this is I. So 0.6 divided by 0.02 will give you the RThevenin graphically, and it is coming out to be 30, whereas experimentally it is 32.85. So these two are close to each other. So from that way we can say that the Thevenin theorem is verified. Are you following? Hello?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
So Thevenin's theorem verified. VLO is equal, nearly equal to VThevenin, and RThevenin is coming out to be graphical value. So Thevenin's theorem is verified. So this is all about the
only thing here are Thevenin, RTH, which we obtained from the graph. Here we didn't put the negative sign, just the magnitude wise.
Magnitude wise.
But actually the slope is negative.
Actually so. That is coming from the equation itself. Now VL is equal to VThevenin minus RThevenin into IL. So from that way. Okay. So this is all about the experimental verification of superposition and Thevenin's theorem. Also, sir, do you add anything more?
No, madam, it's okay. And now only thing is for the superposition theorem, we have given the value of two sources in the video file. So through which, if you wish to, you can just cross check whether you are getting like the way you solve na network theorem. In that same way, you can solve and find whether you are getting.
And
the
all the
same.
resistance values are also shown.
But I am not sure again what is there for the rheostat.
Yes. Very true. Very true. Very true. Okay. So, student, do you have any difficulty? Any doubt?
Ma'am, these slides and video will be uploaded under which experiment number?
One.
Already uploaded. Videos uploaded, slides uploaded. Network theorem 1. Under experiment 1. Yes.
Okay, ma'am. Thank you.
Actually, ma'am, the first video is not completely uploaded.
First video is not completely uploaded. Is it?
We are trying to play. After 10 seconds, actually, it start buffering.
I will upload it again. Okay, no problem. I will upload. Auditro sir. Oh, Auditro sir.
I'll upload it.
Okay. Thank you. Thank you very much.
Regarding the laboratory report, I think we should tell them to write.
So write the report. I think Rajdeep sir will send you the mail regarding report writing, and whatever table we have done for this experiment, you do this, and you also do the graph for Thevenin's theorem. Extrapolate this to get V Thevenin and ISC graphically, and also find out the R Thevenin graphically. Isn't it, Auditro sir? And also the discussion.
I feel they should do it in the graph paper.
Obviously, graph paper. Otherwise, we will not get any accurate values. And also, in the manual, there will be some questions. You try to answer these questions. Why this error is coming? What is
all
the
these
problem?
things are already we have discussed during the interaction, so you will get the clues for them.
Yes.
Ma'am, for data, we will prefer the sheet that you will provide now.
Yes. No other
Okay,
option. No other option other than this.
Okay, ma'am.
We are unfortunate.
Ma'am, is the date of submission already given?
Ma'am.
I don't think so.
Ma'am, we have to make all the 8 experiments in a single PDF.
Is that so? I don't know what is written in that. You better ask
Yes, ma'am.
Rajdeep.
Among the instructions, there is one point which says that all the 8 need to be submitted in one PDF file.
Yes, ma'am.
Then you need to do that accordingly.
Yes, ma'am. Dr. T.K. Bera sir has written in the WhatsApp.
Oh, okay. Then you need to
follow that instruction.
Follow that instructions only. Huh? Okay. So this is all for today. We hope we have been capable to explain you at our level best.
Yes, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you very much, students, for joining. Okay.
Thank you, ma'am.
Okay.
Thank you, ma'am.
Welcome.
Ma'am, when Viva will be conducted? Viva?
No idea when all the experiment will be demonstrated to both the sections. After that, it will be. Auditro sir, should we leave?
Bye, ma'am.
Thank you.
Bye, ma'am. Bye, sir.
Okay.
Bye, ma'am.